Hello, this is David Sloan Wilson for This View of Life, and I'm so happy to be talking with Guru Madhavan, my good friend and wonderful associate. Hello, Guru.
David, thanks for having me. It's a pleasure and an honor.
Indeed, and you are Norman R. Augustine Senior Scholar and Senior Director of Programs at the National Academy of Engineering. That's your day job. And we go back a long way together, all the way back to your graduate students' days at Binghamton University. We're here mostly to talk about your new book, Wicked Problems: How to Engineer a Better World. And so that is, of course, a great topic. And at the same time, your book has takes place in a particular location. Binghamton, New York, is, you might say, a major character of the book, including Edwin Link, um, as the person who invented the first flight simulator. And so, narratively, this gives your book a very pleasant feel. So it's a pleasure to read. And so I'd love you to first maybe outline the wicked problem theme of the book, and then why you chose Binghamton as a narrative vehicle and also dedicated the book to Binghamton. Let's begin there, and then we'll say more about the main topic of wicked problems.
Okay. Thanks, David. Let's first go back to the two phases in my own engineering career, kind of how I've evolved as an engineer over time. I tell my colleagues and the fellows that I mentor that I once used to be a freshwater engineer who now operates in the salty waters of public policy. So there was a migration from one point to another. However, my fundamental training as an engineer was largely focused on the Newtonian philosophy of control systems. A system could be understood in terms of its rudiments, could be engaged with in your terms, that terms set by, let's say, customers, markets, clients, sponsors, and so forth. So every system was decipherable with that confidence. So that was my training in the control systems philosophy. That was my rudiment, which I still try to apply because there's a deep attraction to that concept. I mean, who doesn't want to have an efficient society? That kind of the ability to engage with it in the terms of your design. So that's how I grew up, at least in the engineering tradition. But then my training and my engagement, and especially the fluke elective course that I took under you, because all of the standard engineering courses were sold out for that particular semester.
I'm sorry. I'm going to
Turned
apologize for that right here and now. So
turned out to have a significant impact, and that was, I think, a turning point from me being a control systems engineer to a complex systems engineer. And in the latter part, you can, in fact, the Newtonian approaches crumble in front of the complexity. You have to, by default, take a more Darwinian approach, and that was the motivation that I have kind of honed over time to better engage with the complex systems. So I've lived and worked in Washington, D.C. for 15 years, and I consider myself as one of the few engineers who are involved in advising public policy based on science, engineering, and medical insights, even for public policy for science, engineering, and health. So there is a bilateral flow there. How do we bring insights from one dimension to another? So you constantly have to, at least the kinds of projects that I've been involved in, uh, you have to time travel, so to speak. Time travel, in the sense, how do you engage with these multiple constituencies who bring in very different dimensions to the problem? And it's quite different than a, a system whose requirements are neatly specified. Even if they are not specified at the outset, you can derive specifications to achieve certain measurable outcomes. But increasingly, as I've grown older, as I've gained more work experience, and as I'm trying to make sense of the world, I found myself, in a position where I am pursuing solutions to problems that don't necessarily yield solutions, or evade solutions. Therein kind of begins the initial notions of wickedness. To better understand wickedness, we have to go back to 1965 in a really compelling lecture Karl Popper was giving. He classified the world, according to his viewpoint, into two kinds of systems. There were clock systems that had a greater certainty, greater reliability, and more definiteness and more concreteness. And we all know of numerous examples of clock systems that we live by. On the other side, you have systems that defy logic, and they change character, they change temperament. They're more cloudy systems. So he came up with the neat formulation of clocks and cloud systems. And less than a decade later, in 1973, two scholars wrote a very seminal paper, Horst Rittel and Melvin Weber. They wrote up a paper in a policy journal and coined the term wicked problems. The things that gain more confusion, more character, and more complexity the moment you try to engage with them. So these are the kinds of problems that don't have definite beginnings or endings. There are no clear boundary systems between them. And there is no immediate or final test for a solution, if one exists, for that complexity. And the moment you intervene that system with, let's say, a so-called solution, that will have consequences. So a solution takes on a problematic dimension on its own, and each problem is unique, which means you cannot have a template to deal with it. And that's where your earlier perspectives on the kind of taking the more Darwinian approach or the more evolutionary approach made me or inform my engineering career in a significant way, which means to engage with wicked problems, you need to think about a slightly more elevated, a more informed, a more conscious, a more inclusive form of engineering. And that's how I've kind of cultivated my own career at the junction of engineering and evolution to engage with wicked problems.
Well, I can't help but note the parallelism with economics. And so everything that you said about engineering applies to economics, with the neoliberal approach being very mechanical, Newtonian, based on notions of efficiency and so on, and that being ill suited to real economic systems. So, isn't it interesting that,
In fact, if you go back, some centuries ago, so we're looking at 1700s, 1800s here, how engineering had significant influence
yeah,
in the formulation of what's now
economics?
called microeconomics.
Yeah.
Because it's one thing to build a car, which is a classic engineering problem, but the car becomes an altogether different entity when it is in the midst of a collection of cars, so to speak. So what you now have is the phenomenon of traffic. Now, how do you manage traffic? Is a classic question, and economists puzzle about that. And so we have come up with ideas of not, a classic engineering approach or a more narrow-minded engineering approach would be, yeah, build another road, build another bridge, increase the capacity, and so forth. But then that only takes you so far because you're dealing with the sheer physical limits of the world you're operating in. Then you kind of come into the financialization or the economic perspective of, okay, now how do we do this? Maybe we need to reduce the incentives for people to travel. And that's modern economic speak here. So you start charging people when the demand for some resources at its greatest demand, the demand for its greatest. So then you have the idea of price discrimination as it goes. So you charge differently during different periods of the
Yeah,
day when
this
you're
is one
traveling.
problem leading to another, or the solution to one problem leading to another that you were referring to. So let's bring Binghamton into it. So why Binghamton? Why did you make this such a major character in Edwin Link as part of the book?
Naturally, because I studied there, and the city and the university had such a profound impact on my thinking. In a way, it made me a very different kind of engineer than I was just even a month before. And I think the effects of the Binghamton education um, were enduring to the point that only years later I felt the application of what I learned at Binghamton being put into day to day practice kind of proved fruitful there. And that made me come back to Binghamton to really look back as the world took on a very different shape after the financial crisis, and people started wondering why certain economies flourish better than the others, and the kind of high level policy questions that it made me look or reconnect with Binghamton. There's a current that flows through the book, and we should discuss the kind of the two parts of the book and how they interact with one another.
Please
But
do. Yeah, please do that right now.
the current relates to what could be generally called the politics of recognition. How we choose to recognize the people we ultimately recognize in society, how we choose to recognize the places we ultimately choose to recognize in society. Binghamton, as we know, was once a hotbed of industrial growth, was one of the most highly accomplished economies of one time, and significant community. It was at one point it brought in the industrial legacy and civic legacy together, and I think that that was evident. And so I was deeply captured by that retrospectively, because when I was a student living there, driving past all of the things that I've now written about, I had seldom appreciated their deeper value and significance. So this gave me an opportunity to pay homage. So as I've begin to think about this, this is a love letter to the community. So Edwin Link comes out as a character who's an exemplar of a systems engineering approach that I articulate in this book. What does it take to understand a system in as many facets, if not all of its facets, as possible? Very few people in history were able to practically demonstrate that. And Ed Link, who I argue belongs in the league of the Wright brothers, is virtually unknown beyond the aerospace, and that too, even in a very narrow part of aerospace, especially training and the simulation part of aerospace. It's one thing to build 10,000 aircrafts. We have enough physics to guide us there. An altogether different thing to train 10,000 reliable pilots. And that takes us into the educational aspect. So Ed Link, he didn't write it, or he didn't give talks such as the way I'm characterizing him, but he demonstrated himself to be an engineer who was adept in blending technology, sociology, and psychology. And I think to better engage with wicked problems, you need to have all of these three elements. So Binghamton provides a good tapestry for me to engage with
So
the
just, I mean,
broader.
what Link did was he created the first flight simulator, right? That was his accomplishment. And
Correct.
I guess
So
the building an airplane and training the pilot is an example of your watershed between a mechanical engineering problem and more of a systems engineering problem. Is that safe to say?
correct. So to use his terms, and as I prefer, so he was the originator of the first practical flight trainer. Simulators, the term that comes when the trainers were computerized over time.
Okay.
So a trainer, this was a time when learning how to fly was
Dangerous.
very costly. Yeah, both in real terms and in physical, that you lose life or limb. And Ed Link himself, when he was in California, tried to learn how to fly. And those days, the the teachers, basically showed the controls, and they drove the plane themselves, and the students just had to watch it. And so, how do you get an intuitive feel of how an aircraft works aloft is the question. But then, even more pertinently, it was such a risky thing, as you mentioned. There was a significant crisis in the country, and I go through many different crises that all converged to give Ed Link the opportunity that he ultimately deserved. It was overdue, as well, because initially, when he came up with the flight trainer concept, so his father worked in a piano factory in Binghamton, and this was the time when, before you know, movie theaters and other forms of automated stuff came in. Back then, people just sat and listened to pianos and live performances, or even there was the Link piano company was a world leader at that time.
And
So for the
organs, not
benefit,
not just mechanical pianos, but organs with bellows and air and this kind of thing, right?
exactly. And so what Ed Link does is, like, one day when he was restoring an organ, something, and with this, coupled with this interest in learning how to fly, he was already a newbie pilot, and he sat on an organ component, and he got the exact same feel from that he got when he was flying. So he said, "How? Why not create a trainer, a flight trainer, where it's a planeless mode of instruction on how to fly a plane. So he everything happens on the ground, no damage is done, and you can kill yourself a million times without really killing yourself. And you that's how you learn kind of very iterative evolutionary approach, even. So he came up with what was popularly called the blue box, which was the color of the box, and very rudimentary, had wings, and it pitched, it rolled, and it gave the elementary sensations for the pilots in learning how to get the essential skills. And soon after, with very less what they call the carrier or the transfer of training, so people, when they flew the real plane, they said, yeah, it's just like the Link trainer. So that was the significant accomplishment that he did. And so it took multiple crises in the United States for Ed Link to get his first job or first contract, so to speak. But the real problem happened when there was this national scandal when the airmail delivery. So the pilots who delivered mail, they were crashing in poor weather because they couldn't see. So flying when the visibility was poor was a big problem. Now aviation is an all-weather business. Well, let's say that's what you have to compare. If you were operating a train, you could stop and wait for the weather to leave. That's not the option you have when you're flying a plane 10,000 feet or even higher. So how do you literally bring a blind faith in the kind of the instruments that are in front of you? And I think that's where the pilots started training themselves to develop an instrumental attitude to
Yeah,
deal
you
with it. So
rely on
now aviation
rely
is
on
one
the
of the
instruments, rely on the instruments, and not your own senses,
it's
basically.
on your instincts. Yeah, exactly. And how do you train yourself so that you can supplant the instincts, which can often be faulty because you think you're going in some direction, whereas you're actually, going down and about to crash. So these were really complicated problems. And as I noted earlier, the the problem that EdLink was tackling squarely mixed the technology aspects. He was a pioneer in that, of course, as an engineer. The psychology aspect. How do you trust a system that's slightly beyond your control, not even in your control, and when you can't see anything, just feet away from you? And in modern context, with the civil aviation mushrooming to the size it has ultimately done, you have lives at stake here. So I think it's a highly regulated system and whatnot. And finally, the sociology of it. How do you create a reliable system that people ultimately trust and pay for? So that's what I think EdLink did, and I wanted to pay homage to his systems thinking throughout this book. And of course, Binghamton provides the natural backdrop for EdLink's story as I go through many different adventures that EdLink had. Ed also had a very interesting dimension because at the peak of his career in flight training, he decides to quit flight training and goes on to an entirely different medium, deep sea diving. And he gets very interested in underwater archaeology, and he starts exploring possibilities to live under the ocean, hundreds of feet below, and what possibilities exist and so forth. Now, this person, you know, was unafraid of mediums, was unafraid of the potential complexity each of these medium offered. So he did ground-based simulators that ultimately helped astronauts go to space and ultimately land on the moon. So from the ground to deep space to deep seas, he really transcended the mediums here, and I'm naturally attracted to that sensibility that I think we should all at least begin to appreciate a little bit more.
And one of the appeals of all of this for me is that I think that the idea that Binghamton, celebrated for its past, could actually become noted as the city that solved adept at solving wicked problems based on what we know now about wicked problems in your book and so on. Binghamton's future can be bright as a city and university that is adept at solving wicked problems. And so I think that you and I, with our Binghamton connections, can help to make that happen. But let's return to the theme of wicked problems and follow the outline of your book. You have these evocative chapter titles. So we have wicked efficiency, wicked vagueness, wicked vulnerability, wicked safety, wicked maintenance, wicked resilience. Civicware is your epilogue. And sandwiched between them, you have your refrains, which bring us back to Ed Link: pitch, roll, yaw, surge, sway, and heave. And so I don't think we can probably cover each and every one of these chapters, but lead us through the book. Now with a focus on wicked problems that anyone can appreciate, not just people with a Binghamton connection.
Sure. Let me get to the design of the book itself, and I took inspiration from kind of the musical structure because Ed Link's career grew from the music industry, the pianos and the organs and so forth. So I tried to structure the book as a musical counterpoint to interacting harmonies, producing an altogether different effect than what they could individually produce. So we talked about Ed Link, so let me just attend to the refrains right now. Adlink's flight trainer ultimately evolved into extremely sophisticated flight simulation systems that now are the default for training pilots. And now we have simulators that operate at 6 degrees of freedom, as they call it. So these are the states that an aircraft can exist. And these are different physical motions. So an aircraft has three rotational elements and three translational elements. So that's what the angles are. What pitch, roll, and yaw are the rotational angles, and the surge, sway, he are the translational angles. So good pilots are trained in all of those 6 dimensions. So that's why I used those titles for the EdLink sections. The parallel is, of course, the book, and as I mentioned earlier, EdLink and the systems engineering philosophy. Now, how do I bring it to use, adapt it, rework it, perhaps even for understanding contemporary wicked problems? So the main theme of the book is about developing a concept of operations. It is a very important systems engineering tool, what in the trade we call as ConOps. which is the first step. These are narratives um, to understand scenarios that don't exist yet. And in a more specific way, these are to understand how a system works and how it should desirably and responsibly work in other different instantiations. So, what I'm arguing is to better engage with wicked problems, which society is filled with, we need an engineering concept of operations. So, the six chapters are filtered through the six concepts that you had outlined: efficiency, vagueness, vulnerability, safety, maintenance, and resilience, which I have articulated as a set of concepts that could, in conjunction, provide a greater perspective into the problem set that we are trying to engage. But wicked problems aren't straightforward, as I mentioned earlier when I was defining them based on the classic work. Uh, this is where I started thinking about now what exactly is the inner nature, inner character of wicked problems, because definitions alone seem unsatisfactory. So you have to really engage with the constituent elements here. So there are sorts of problems. This is where I kind of mix Rittel and Weber's work with Karl Popper's work, and I fuse them together to come up with the formulation of there are classes of problems that are bounded and boundable. So these are hard problems. Let's say you check into an airline from your cell phone or do automated checkout in a grocery store. These are all like tried and tested, straightforward problems. You can optimize them to the hilt to achieve solutions. So a hard problem can literally be solved. They can result in solutions, as I said. The second class of problems are when you when a hard problem is complicated by political and psychological influences. You have what you call soft problems. That's we talked about traffic management earlier on. There is no solution for traffic, as we know, that works clear cut across context. There is no universality there. So you can only satisfy those solutions, and instead of optimizing them, you can
Why
only
would
take it to a
why
point.
would you call that soft? Just to pick a point. What's soft about it? Why do people
Yeah,
use the word
it's
soft for?
it's actually harder than hard, but I think it's perhaps it gains a little bit of mushiness is what I'm trying to take it. Take yeah, one has to if you want to use an artistic metaphor here, it's like the kind of the blurry impressionistic imagery that you know something is there, but you can't quite pinpoint it. Unlike, let's say, a photograph or a sculpture, which is a hard problem. So you can only satisfies them. So a soft problem cannot be solved like a hard problem. Instead, it can only be resolved. Now, a soft and a hard can interact, and that's I think that this is where the complexity concepts come in. And at a higher level, you have messy problems. So this is where things get complicated because of our value systems and what we believe in, and how we scope and shape our problems, which are all culturally dependent, contextually dependent. So a messy problem can only be idealized because it has enough complications that you can't really brute force it to result in solutions or resolutions like hard and soft problems. A messy problem can only be dissolved, which means you have to transform it to an idealized state. So you have hard problems, you have soft problems, and you have messy problems. Hard problems can be optimized, soft problems can be satisfied, messy problems can be idealized. Hard problems can be solved, soft problems can be resolved, messy problems can be dissolved. Wickedness comes from the interaction of hard, soft, and messy. So when we say that we can solve wicked problems, we are actually just meaning that we are only solving the hard problems within the wicked problems. So a wicked problem needs to include solutions, resolutions, and dissolutions. And I think that's how you manage it, knowing what wicked problems are capable of doing, which is to become something else. So this is about how to effectively manage the system. To go back to your own writings, David, on cultural evolution, how do you cognizantly manage a culture?
Yeah, well, let's pick one of these, and I want to pick maintenance because I think it's such a fascinating concept. And as you point out, this is going to be coming from you in a minute. We place such an emphasis on innovation and change, and maintenance is just that's the guy with the broom that's walking down the hall with the broom. But think again and how amazingly important maintenance is. If you could expand upon that theme, one of the high points of the book for me about why maintenance deserves much more respect and attention from us than it gets compared to innovation and change.
So I did a business degree along with my PhD in Binghamton, and since that time, and subsequently, I keep myself abreast of the business literature and whatnot. And in Washington D.C., the conversations about prioritizing innovation is almost it's a perennial topic. So much so that some years ago, I had this revelation about the are we overemphasizing innovation, perhaps at the expense of something else that is crucial within engineering. And I think if you look at the statistics of it, but 70, even 80% of engineers work in operating and maintaining existing systems. They don't uh, work. In fact, people who are in innovation and R&D are only a minority of the entire engineering enterprise. Yet, that work, however crucial, gets the most press, and the rest of it is not in the news. And I that kind of made me think about what a, how we are perhaps focusing on competition over care, over the more dazzling acts of creation than the dull acts of conservation. So that kind of ties back to the politics of recognition, how we choose to prioritize one act over another, perhaps at the expense of another. And that's made me connect with some historians who are also thinking in the same line of the arguments. I started writing some pieces about it, and that motivated me to insert a full-fledged chapter on maintenance as part of this concept of operations that we all need to consider. So, um, biologically speaking, of course, we all know the importance sleep
Yeah, that's
has
when you're a
for.
biologist, you know how much of the energy budget of an organism goes to maintaining it. That's what it means to stay alive.
Correct, and
Um,
many of these chemical reactions, they're all happening um, based on processes that are billion years or old. I mean, these are the dull, diligent processes that keep our survival, going, even our civilization functioning. Also, I can see significant religious connection here, how people try to prioritize maintenance at the outset, even way before when we were trying to form civilizations and so forth. And David, I know you have studied very extensively religions uh, and their value to society. I come from an Orthodox Hindu family in South India, and my earliest appreciation of maintenance began with my grandfather, who was a local temple priest in our village. And every few or so years, we would renovate the temple, and the entire community would pitch in. They would join in the festivities to renovate the temple. So it was a act of cultural unity, cultural belonging. Even though, from a structural engineering standpoint, it was just kind of upgrading the building. But we even in Sanskrit we even have the concept of jirnodhara. Jirna means digestion. Udhara means advancing. So you digest and advance. So you can see the biological connotation of it. This is what happens during sleep. It's the kind of the surprising self renewal that makes our survival possible the next day. I think I'm increasingly having issues when innovation is being branded as the heartbeat of the global economy.
yeah.
I think maintenance which are the equivalent of sweat gland or sweat glands, really. I mean, you can think of all the complications when you don't sweat. I mean, it doesn't matter whether you have a heart rate or not. So it's
Well, you have an
that's how integral
example.
they are.
You have an example, if I remember correctly, of I think it was a music hall or something in the book. Is that am I remembering correctly that you used as an example of like this beautiful, beautiful concert hall, and
Correct.
then and then everything that was required for its maintenance, but also, and this again was um, a wonderful insight for me. If you did want to change it, if you did want to innovate, you couldn't do it without an intimate knowledge of its maintenance. The current
Correct.
system is the starting point for change. And so you can't just change without knowing what the current system is. And so
Exactly.
actually,
People
maintenance and
people often think
innovation are
that
joined at the hip.
yeah, people often think that maintenance doesn't involve change. In fact, it's as much or more change than innovation. In fact, it's an enabler of innovation. And
Yeah, that's what
um,
an equilibrium is about. It's what a thermostat does. It changes in response to and so on and so forth.
since we were talking about pianos and organs in the different track earlier of Ed Link, I use a metaphor here. Um, Beethoven, you know, basically helped the manufacturers of the pianos that he used to maintain them better because he was using the piano so aggressively, so frequently. It gave insights to the manufacturer on how to maintain them better. So I think you can see great innovations from Beethoven came because the piano operators and he himself knew how to maintain the piano that he was working on. So I think that's how legends are created by the kind of the boring, diligent acts of a commitment that we have.
Yeah.
So maintenance is just one such important aspect that we frequently forget, and I just wanted to make it as part of this integral considerations.
Well, let's cover one other chapter topic. I might pick. I mean, you should pick. Resilience is one that I might pick. But which one, just to pick another chapter topic, would you like
So
to dwell on?
let's pick two for just comparison. These are the first and the last chapters, so they're not necessarily uh, the kind of the bounds of the concepts here. But as I mentioned earlier, I was brought up in the Newtonian tradition of controls, right? And so the ultimate objective, oftentimes in many industry domains that I worked in, was about achieving greater efficiency. And efficiency was the end point as I was trained early on. But here, I just inverted the question: what if I make efficiency as a starting point? If so, what becomes the destination? So each of these six concepts are not ranked in any hierarchy or so. They need to they need to work in combination. Each of them is profound on their own, but together they create a even more profound set of insights here to deal with. Each of these concepts have their hard, soft, and messy dimensions, and that's why you have chapter titles as "Wicked Efficiency" through "Wicked Resilience" here. So that's what I think we need to aspire toward to get a better sense of what we're dealing with. With efficiency, as I said, um, who wants to live in an inefficient society? I mean, like we are all creatures of efficiency. It is the dominant doctrine of engineering, as it has always been. It is the basic preference of humans as more technological sophistication comes to us. I think we expect greater efficiencies in that. So we are all beneficiaries of hard efficiencies, as we have discussed earlier when I was describing the problem sets. But uh, they can also take on more complicated dimensions. And we touched on the concept of price discrimination earlier. But whether it is charging people for using a bridge or a tunnel at a particular time of the day, or how do you go about pricing prescription drugs, which is where the concepts of fair pricing come in, and this is an age-old concept in economics. going back to Adam Smith, and how one thinks about it. And commonly, economists or engineering informed economic theory came down even comes down to the conclusion it's ultimately about what people are willing to pay for a service. 25 bucks to cross Verrazano Narrows Bridge one way, sure, I'll pay it if I can avoid the traffic in going north on the New Jersey Turnpike. So that's, I think, a choice that I make. It's largely personally derived. So that's kind of a softer efficiency one has to confront. The messy efficiencies can be in the form of you know cultural rituals that have been in place for thousands of years. And David, I know you have studied um, uh, the Ebola crisis and offered your perspectives on it. And I think from our respective studies, we know how important the local burial rituals were in and how they instigated the transmission of the virus because of people's belief systems. And so, how do you engage with that system? How do you idealize it? How do you transform the system where people can still pay respect to the deceased, and while curbing the infection? And that's where you need to come up with more safe and dignified burial rituals, and that's simultaneously an evolutionary or anthropological and an engineering solution that plays hard and hard. So that's what, so you get a perspective of the hard, soft, and efficient, messy efficiencies at play here. To go to resilience, which is how I end the book, um, it's such an overused word in modern life to the point it comes up in every other meeting that I'm in on a daily basis. And people are trying to figure out what should be the nature of work, future of work at the highest levels of corporate affairs, and resilience is the thing. And it also comes in people who are care providers in healthcare. What kinds of resilience should people um, aim for so they can care for patients and take care of themselves, so they don't burn out and so forth. So it's at many different levels. Economies need to be resilient, supply chains need to be resilient, whether you're making paper clips or masks or battleships, everything has to be resilient. So it's everywhere. But if you look at how even the concept came in from an engineering sense, it goes back to basic woodwork carpentry. When people are trying to understand how different types of wood perform against different stresses and strains, so they could build better, more resilient ships. But of course, philosophically speaking, it's a much older concept. It goes back to Hindu scriptures as well. We have resilience illustrated. How do you develop a still mind? How do you do wakeful meditation? How do you prevent yourself from outer influences? So that, I think, it's kind of goes back to the metaphors of the resilience of a grass against the winds. A larger tree can be uprooted, but a grass is more resilient. So I think there are some human dimensions to resilience. So I just wanted to go back to the fundamentals of what resilience means and explore them in the hard, soft, and the messy dimensions. So resilience, according to the journey of this book, is number six in the collection of six concepts, but it is not sixth in a rank order.
Yeah. Well, here's how I want to end up, Guru. Back in Binghamton, one of the things that I'm hoping to do is to basically uh, conduct a poll of Binghamton residents. What are some of Binghamton's wicked problems? What do you think is a wicked problem in our city of Binghamton, New York? And let's say that we did that, and then we were to get a list, and then how would we proceed to, now we don't want to use the word solve because they're wicked problems, but make some kind of progress on these wicked problems. We've already chosen one, which is homelessness. And we just had a meeting with our team that we've convened earlier today on and it was fascinating working with an organization called Community Solutions, how systemic
Correct.
they were. If you want to solve a problem like homelessness, you have to create a whole system around it with all of the stakeholders, and then all of those stakeholders must be trained upon each and every homeless person is the way that goes. But in more general terms, to make this bring this down to earth, a little bit less abstract, can you imagine some process whereby, first of all, members of the community nominate wicked problems, and then we initiate some systemic process to make them better? How would that go? I mean, how would you uh, make progress on that front? Because I really want to do that. I want to do that with you and with other people, our associates in Binghamton, so that Binghamton can once again become known as a, and here I'm using the word innovation, uh,
Mhm.
in terms of an innovator in solving wicked problems.
And appropriately so, because as we touched on very briefly earlier, the industrial legacy of Binghamton can provide such motivation. And it was, if you look at the world-renowned companies that were founded in Binghamton. At one point, the Endicott Johnson Shoe Company was providing shoes for
For the
all of the
world,
world, and
world's
then
largest shoe
IBM,
manufacturer of its day,
right? IBM was founded as just a
IBM.
couple examples, and I think in a significant way, those companies um, diminished the borders between factories and communities. And I think the founders of those companies were as communally involved, not just running things from from afar, as most modern day businesses happen. And Edlink also followed that track. He was deeply loyal to the community. He was ultimately very proud to be a Binghamtonian for the rest of his life. And even in his waning days, he was fixing organ systems. He went back to where he started and
Yeah.
and he didn't even have parts to assemble or
Well,
fix an
let
organ.
me add a sad note to that. Knowing Binghamton as well as I do, that you're right that IBM and Johnson and Endicott um, shoe companies were very communitarian, but they were also very paternal.
Mhm.
And then ultimately, whether due to economic circumstances or due to a change of leadership, they left the community.
Correct.
And it's been said many times, and I believe it's true, that the primary ethos of the city of Binghamton, cultural ethos of the city of Binghamton, New York, is of having been betrayed
Mm.
because the benefactor, the paternal company, just abandoned the community. So it was it was paternal and communitarian, but it was in a top-down way that we don't want to repeat. There's lessons learned from that, having to do with such things as resilience. Next time around, we want our businesses to be communitarian in a way that doesn't lead to that problem. So I think that's a very interesting lesson to be learned there, much in line
You're
with the
absolutely
concept
right,
of wicked problems.
and that's the kind of that was the line of my thinking here, because people have been trying to rejuvenate, even revive the economy that was lost because of significant departures just a couple of decades ago, even. So, how do you rebuild an economy? That is a wicked problem here. It has hard aspects, it has soft aspects, it has messy aspects. So, it's not economics stimulus through financial infusion. It's a technological fix. It's a spot solution. You can achieve hard gains from it, but they may not be durable. So that's why you need to take a more evolutionary approach, literally, to kind of in alliance with the systems engineering concepts that I was talking about. What is the fundamental concept of operations to revive Binghamton's economy? What are those elements? And if you try to engage, or if a group of us, or try to engage with this problem set using the six concepts, each from different lenses, I think our appreciation and understanding of the deeper complexities and the nuances become clearer, rather than just relying on public officials who are already probably have too many things going on, and they're just oftentimes one or a few people running are responsible for
Yeah,
a city. So I think,
just to let our audience know, I mean, one of the things that makes this so entertaining is that our good friend and colleague Hadassah Head, who's part of our tribe, is now the president of the city council, and so we're getting involved in local politics, and so getting a firsthand view of how that should be the solution, but also could be very much part of the wicked problem.
correct. And
And
let's say we
so
even
it's
bring some of your former students, including Hadassah, so to speak, and we get together. I think our uh, the way we collectively come to even the idea of consensus building. How do you achieve it? So this provide, I mean, in systems engineering parlance, systems engineering works sometimes the best when it is not expected to produce an engineering solution. And I think some of the wickedness we are facing culturally, whether it is reviving a city or achieving housing goals in a community or reducing drug problems, these are all, I mean, if you look at writings from 100 years ago, these are all still there. And I merely took that as a kind of a challenge and see what I can contribute in terms of an architecture, so to speak, to this engagement. So, economy is something that's been talked about for a long time. People are leaving the area, and I think um, now, how do you to revive the economy, to boost an economy? You need to have people coming in, willing to contribute to the economy and the civic life. So, how do you make it an attractive place that was once attractive? I mean, there was even a poster called "Which Way EJ?" So everyone, people from immigrants from Europe would come to Staten Island and go straight up to Binghamton because they all wanted to work for EJ.
It's the only English phrase they knew. Which way, EJ?
Yeah, exactly. And of course, homelessness we're talking about, but also climate change, which is one of the biggest subjects that we all hear about every day. There's hardly a newspaper that doesn't write about it. Uh, what is Binghamton's contribution to it? I mean, contextually
Yeah.
speaking,
And we have a
and I think
colleague,
that's a good.
Andreas Pop, in the economics department, who's part of our team, who's headed a program called Binghamton 2 Degrees.
Mhm.
What will Binghamton be like when it's 2 degrees warmer? What could be done about it? One of the points he made to me is that actually, climatically, this region of the country is going to be a climate haven. In other words, as it warms up, it's not going to be that bad. And so, therefore, it'll be a location where people resettle, which is quite a fascinating twist.
So, what are the
On
policy choices we all need to take? And that takes us back to the flight simulator. So, how do you, um, fly the plane without crashing it? So, without
Yeah,
needing to write
and
a check
that's where.
for those policy choices. So, you can do these offline and envision these different future trajectories.
Well, I
Uh,
find it a lot like weather forecasting, and here's where simulations come in. Happens to be Andreas's specialty, and makes a tie back to to link. Then complex systems, and of course, weather is a complex system, and so you can't predict it um, with any accuracy. So what do? You have all these all these weather models, and you test them against each other, and then you perfect them, and it's just an ongoing process with your weather models. Well, if there's social complex systems and other complex systems, you need that too. And
correct.
so you need exactly that. And so there's the whole simulation component that that's needed for our social complex
This
system.
aspect of systems engineering is less recognized because most engineers, at least I know, they run away from contradictions. I used to do that too, but I think over time I've gotten more attracted to them. So systems engineers actively embrace them because you have all these different kinds of models, viewpoints, requirements, schedules, and whatnot. That's where systems engineers are really good at focusing on three elements, which I've described in the book. First, just to focus on the essential sensitivities, which is like what a particular action does or could do in terms of an effect on something else, and this is the foundations of complex systems thinking, as we know intuitively. But the second is also synergies, and I think from your writings on cultural evolution, it's pretty evident where multiple actions can jointly provide a benefit, not necessarily in one domain, but perhaps in another or across different domains. That's something we need to do further work in kind of improving that competency, identifying these synergies. The last one is, of course, side effects, because what if something bad happens here? And like speaking of Binghamton's wicked problems, like let's say company X, it's a startup, leaves town. What happens to the broader economy versus a big employer leaving? And I think those are just simplistic illustrations for the point here. So sensitivity, synergies, and side effects. Imagine a group engaging with the concept of operations and looking at these aspects. And I think to better engage with wickedness, I'm increasingly convinced that a systems engineering approach that is informed by evolutionary principles, philosophical insights, historical information could be very fruitful in providing an elemental structure here.
Yeah, and I think that some of our listeners might be surprised that the word evolution hasn't been used much, um, um, but it really has in the background, because in what we can see, and we've written on this, we have a podcast on this we could provide in the liner notes, but this kind of systems engineering is a highly refined form of systems level cultural evolution. It's inherently experimental. You never optimize the whole system by separately optimizing the part. You almost must have the welfare, the whole performance of the whole system in mind as you make your change, and so on and so forth. And so it's deeply evolutionary. And I think that so interesting that your experience at Binghamton kind of led you to that.
I think we have our further discussions, and I think we casually talked about during a break at a major policy summit in Berlin, I believe, and you and I ended up writing a paper about the incessant focus on complex adaptive systems. So much so that it's we are overproducing literature in that area to the point that there's no discussion on complex maladaptive systems. And I think I again as part
I
of
mean,
my
but,
basic
Guru,
engineering.
let me reinforce that. Exactly what we did is we typed in complex adaptive system as a search term. We got over 1,000 hits. Then we typed in complex maladaptive systems as a search term, and we got 0 hits. And it's like, what? What is going on here? That this the whole concept of a complex system, which is maladaptive, which is the typical case,
I think
amazing.
the trouble begins right because first there's not much recognition of this. Number two, people who use the term complex adaptive systems confuse with their different varieties. As we have argued, there's complex adaptive system type one, where the system itself self-organizes to a broader
It's a
objective,
system
and I
that's
think
adaptive as a system. What would you think?
correct.
Complex adaptive system, a system that's adaptive as a system compared to type 2.
Correct. And where the individual agents or the groups try to um, optimize their own behavior or their outcomes here. This is something this was just instilled in me from the get-go. Systems engineering courses. I wish this becomes a tagline and people really consider it in their daily life. You cannot optimize a whole system by optimizing their parts separately.
Yeah,
This is the
cannot.
founding doctrine of systems engineering.
Yeah,
And I wish this was more popular and people would appreciate it. But
it will be. It will be. I think that one of the things that I've discovered is that these ideas, which are so simple after you master them, are also so new that otherwise brilliant people, well read, well informed, open minded, they just haven't encountered it yet. And so I think that there's a simple contagion model that we need to follow of just spreading these ideas. And the more we do that, the better the outcomes will be. Now, Guru, I want to end with the event that's planned for March 17th. So if you're in the Binghamton area, and maybe you even might want to travel to the Binghamton area, then on March 17th in the afternoon at the Roberson Center, you'll be lecturing. And it's a lecture sponsored by the Link Foundation, if I recall correctly. And then afterwards at the Lost Dog Cafe, one of our finest eateries and drinkeries, there will be a social event following the lecture in which we will speak and we'll have a chance to lift a glass with our friends in Binghamton. And then on Monday in Binghamton University, you will be giving the EVOS seminar, co-sponsored by COCO, which is our Complex Systems Institute. So I think this is the kind of dust we're going to be kicking up in Binghamton on March 17th and 18th. And I cordially invite everyone within traveling range to join us.
I'm most nervous about the last commitment to give an EVOS seminar because I once used to be a student in the EVOS series and I've attended seminars and several luminaries have lectured in that series. So very honored and quite nervous. But thanks for the invitation and I hope I'll get to meet many of synergistic thinkers here.
Awesome. Okay, and so we'll make Binghamton the city and university that's adept at solving wicked problems. Model city on the hill for other other cities to follow. So thank you, Guru, as always, and we continue to work together.
David, thank you so much. It was a fun conversation.
Okay, bye bye.